Hello everybody. So in this video we're going to do an example of checking that a function satisfies Rolle's theorem and then looking for the C that's given by Rolle's theorem. And then we're going to talk about why it's so important to actually check these hypotheses. Okay, so let's look at this example. Okay, we are going to verify that this function f of x satisfies the hypotheses on the interval -1 to 3. Okay, and then we are going to find the C value that is guaranteed by the theorem, right? So we have Rolle's theorem up here on the left, okay? So let's start this problem, and we are just going to start checking it 1, 2, 3. Okay, so the first thing we want to check is that this function is continuous on the closed interval. Okay, so we would say that f of x, right, is a polynomial. So one of the things that we learned in chapter 2 is that polynomials are continuous on all of the real numbers. Okay, so f of x is continuous on all of the real numbers R. Okay, now that's not good enough, right? We want to check this hypothesis specifically. Okay, so we're going to elaborate. So we're going to say specifically f is continuous on -1 to 3. Okay. Then we're going to check the second hypothesis, right? F is differentiable on AB, the open interval. Okay, so we're going to look at f prime of x. Now in this example, we can just say what f prime of x is. So that would be 4x minus 4. Okay. And f prime of x, I guess we don't want to say and, okay? We'll say so, right? By looking at it, we can determine that it is a polynomial. Okay, what that means for us is that f prime of x exists everywhere. Right, it's defined for all x. okay? Specifically, the one that we are interested in, f prime of x exists on the open interval -1 to 3, okay? Remember, saying that f is differentiable and saying that the derivative exists mean the same thing, okay? Now, we do want to be this specific, right? We can't just say that the polynomial is continuous everywhere, right? We want to specifically say that the function is a polynomial, so it's continuous everywhere, and specifically on -1 to 3, right? The derivative is a linear function, which is a type of polynomial. So that function is defined everywhere. Specifically, it's defined on this open interval, -1 to 3. Okay? Now we have to check the third condition. We need to check that f of a, right, f of -1 is equal to f of 3. Okay? So f of -1 is going to be, we're just evaluating the function at the endpoints. Okay, so f of -1 is going to be 2 plus 4 plus 5 is 9. Oh, I'm sorry. 4 plus 5 is 9. 2 plus 4 plus 5 is 11. Okay, and then f of 3 okay, so this is 18 minus 12 is 6 plus 5 is also 11. Okay, now again, it's obvious that these are equal, but we want to be very specific when we're verifying this. Okay, so f of -1 is equal to f of 3, right? This is what we're trying to check. Okay, so that takes care of the first part of this, right? Verify that it satisfies the hypotheses of Rolle's theorem on -1, 3, okay? That's what we've done so far. Now we want to find the C value that's guaranteed by the theorem, right? We want to find the C value in the interval -1, 3 so that f prime of C equals 0, okay? So we are looking for C in -1, 3, right? Oh, I'm sorry, in the open interval -1, 3. So that f prime of C equals 0. Okay, so let's go ahead and find that value. Okay, so f prime of C equals 0. What is that going to look like for us? We're going to have 4c minus 4 equals 0. Okay, so C is going to be equal to 1. Okay, so this is the x value, C, that is guaranteed by the theorem. Okay, now let's take a look at what's going on graphically in this example, right? So we want to look at this function 2x squared minus 4x plus 5, and we want to see where the derivative is 0. Now visually, we are looking for the place where there's a horizontal tangent line. Okay, so if we look at our function, right, our function 2x squared minus 4x plus 5, that's the blue parabola, and we are looking for a place where this tangent line is going to be completely horizontal, right? So as we look across, here we go. Here is the value, right, where our tangent line is exactly 0. And you can see, right, when we look at the x-axis, that this is exactly at the x value 1. Okay, because this is a parabola, we're looking at the vertex where we have our horizontal tangent line, right, or our derivative is 0. So this is really what we're doing in this problem. We're checking that the theorem applies to us, okay, and then we're scrolling through all of these values between -1, right? So we're starting at -1, which is here, okay, and then we're looking through all of the values until we get to 1, right, between -1 and 3, where we have a horizontal tangent. Bam, there it is at x equals 1. Okay. All right. So now that we've looked at a basic example of how this theorem works, what we're checking for, and especially what it looks like to check for that, let's go ahead and talk about why it's so important to actually look at the hypotheses, right? Why can't we just conclude things without checking these 3 things so carefully? Okay, so let's look at our second example. Okay, so we're looking for a function that is continuous on the closed interval 0, 8 and differentiable on the open interval 0, 8, but does not have the derivative being 0, right? No horizontal tangent line for any c in the interval 0, 8. Okay, so I encourage you to pause the video now and draw yourself a function that satisfies this. There are tons of different functions that satisfy this. Okay, and we want to look at just one of them. Okay, so I want something that is continuous on the closed interval, meaning I should be able to draw it on this interval without picking up my pencil. Okay, I want it to be differentiable, meaning it should be smooth looking, doesn't have any cusp points, any discontinuities. Okay, but I don't want a horizontal tangent line. So to me, the most obvious choice is just to pick a line, right? This function is surely continuous. It certainly has a derivative at every point in this open interval. In fact, we know that for a linear function, the derivative is a constant, okay? But there's nowhere here that the derivative is 0, right? And we know that because when we look at it, there's no place for a horizontal tangent, okay? And this is so important. This is why we need the third hypothesis, right? You'll notice that when I drew my line, right, I drew it as an increasing line, right, meaning that f of a and f of b, right, f of 0 and f of 8 are not equal, okay? So this is why we really need to check that third hypothesis, right? If the endpoints don't have equal y values, then this theorem just doesn't apply, okay? It could be as simple of a function as a linear function. Okay, let's look at part B of this example. Okay, so we're gonna try to draw a function like this. And again, I encourage you to draw this function now yourself, right? Pause the video and think about what this function would look like. Okay, you've got the endpoints being equal in value. They should be at 1. Okay, so I have that f of 0 is 1 and f of 8 is 1. Okay, and I also have that the function is continuous, which means I should be able to draw this without picking up my pencil. Okay, but I don't want to have any place in this interval 0 to 8 so that f prime of c is 0, right? Meaning no horizontal tangent between the two. Okay, now one thing that comes to my mind is to draw something that does go up, but when I go to come back down to connect to my other endpoint, I don't want to curve it back down and slope it, because that will make a place where, that will make a local maximum, right? And it will be a place that we know the derivative is 0 because there's a horizontal tangent. So I'm actually going to form a sharp corner here, right? A cusp point, because I know that there is no derivative being 0 at this point. The function is not differentiable here. Okay, And this is why it's so important to check hypothesis B, right? Or hypothesis 2. Right? The function can go up and come back down, or go down and come back up without having this local maximum or minimum if you create a cusp point where the function isn't differentiable. Okay. All right, let's look at part C of this example. Okay, so in this part of the example, we're looking for a function that is differentiable on 0, 8, 5, 6, 7, 8. Okay, and the value at the two endpoints 0 and 8 are again equal. They're at 1. Okay, but we don't want any point in 0, 8 that has a horizontal tangent. Now, before you pause the video to try to draw this function yourself, I want to remind you that if the function is differentiable on 0, 8, that means the function is also continuous on 0, 8, right? It is a more strict condition that the function is differentiable than it is to be continuous. So we know that the function is not only differentiable on 0, 8, it's also continuous on 0, 8. Okay, so I want you to go ahead and pause the video now and think about what this function would look like. Okay, so we want the endpoints to be equal at 1, so at 0 and at 8. Okay, and then I want the function to be differentiable, which also means continuous on the open interval. Okay, now I am going to draw basically the same function that I drew for the first one, right? I can see that there is no place here where there's a horizontal tangent line, right? And I'm going to draw a big empty circle at x equals 8, okay? There's no point along this interval 0 to 8 where the tangent line is horizontal, meaning that the derivative is 0, okay? But I still have a function that is differentiable on the open interval. Okay, the issue is that the function is discontinuous at one of its endpoints. Okay, and this is why we need to check that very first condition. Right? In some ways, this is the most basic condition. We must have a function that's continuous on the closed interval to even begin looking at whether it satisfies the other criteria. Okay? So this is why each of these three hypotheses are absolutely necessary to conclude Rolle's theorem. And when you see in the next video some examples of proofs that use this theorem, we're going to be very particular and very precise about making sure that we are checking these three things and that we're checking them correctly. Okay? So I will see you guys there.